thanks, Mike, for that introduction. I'm going to talk today about what we've done at Northwestern to improve the graduate education. The let's see, what's going on? I'm trying to record this, so I've got a little bar there. So we've got this course at Northwestern for organic chemistry graduate students. This is pretty common among all sorts of major institutions that have graduate students. And the synthetic chemists, they come in, they've got to be prepared for their life as a chemist, or at least for their graduate experience. And so they take this course where we include NMR and mass spec and IR and X-ray. So it's a very multidisciplinary course. They need to know, basically we have a series of basic, fairly basic goals. They need to know, we need to train them to get them to the point where they need to know what experiments they're going to run, how to set up their experiments manually and in automation, how to analyze their data accurately and efficiently. So they need to crank through all kinds of stuff. One of the constraints that we get is that these are not people who really care a lot about NMR. These are people who are out there to make molecules. They want to make stuff. So they a lot of times they're coming down to just verify what they've made, right? So so we need to show them what they can do as a practical matter. And they're not going to be that interested in, say, theory. Like if they start seeing vectors, then that gets scary. The mechanics of our course is that we meet a few times a week. We are on a quarter system. So actually, they only get 12 lectures on NMR, a few homework assignments, and a few labs. And from that, they've got to go off and be on their own. Okay. So this year we wanted to include software in the training. Before we just kind of handed out photocopied sheets of paper or something like that, or we said, okay, use problem 5 out of the book. So this year we decided, we're going to use software because that's what they're actually going to do, and this is how how to prepare them best for their work. We've got to figure out what kind of software we're going to use. So what are our design criteria, or requirements? First of all, it's got to read both Varian, Agilent, and Brooker data because we're a poly vendor shop that we've got all these different instruments. So the software, whatever software we choose, has to be able to read all this data. It's got to be cross-platform. So if we take a look at our class, about half of them are using Macs, about half of them are using PCs. So any solution that was just a single platform just isn't going to work, or would be so unpopular as to fail miserably. It has to be affordable. So we can't actually say, all right, you guys, you've got to go out and buy your own software, and it's going to cost you $800. No, that's an easy way to get people to be very unhappy with you, to write you terrible reviews about your course, and to not do their homework. So instead, we do have this resource, the Office of Research, where we can apply for money to fund such a thing. Okay. One of the other essential things here is that the students have to find the software desirable. Like if they start using it, even if it's really useful, if they just don't like it, they're still just not going to use it. So we needed to take that into account. And it turns out that they had actually asked for Mestrelab. The Northwestern has a kind of a user senate where they have representatives from the different groups, and they kind of all got together and they stepped up to demand that the lab purchase Mestrelab. So we did. How do we use it? So what are we going to do with this stuff? The traditional old school way of doing this might be to install the software on a bunch of facility computers and have everybody come down and use that. But we have just a few. We don't really like to maintain a large number of computers that way. And so that wasn't so attractive. Do we want to install it on a server and have people use it by remote desktop? That again, that's inconvenient. That can be difficult to get people who don't really love computers to actually adopt such a thing. So instead, we're going to use the students' own laptops. If this is 2012, you can assume that that basically everybody coming into the course, every student, is going to walk in with some kind of a laptop. They're taking them with them everywhere. They bring them into our lab, and they're using them all the time. So we're just gonna have capitalize on the resource that already exists. Okay, so we have this concept, that if we were teaching a course, you can require a textbook. So let's require software. So this is just a snapshot from the course syllabus, where we just state it blithely, required textbooks, required software, and they've got to get it. Okay. So the next step is how to train them. It's one thing to say, okay, everybody, you've got to all download your software and you've got to install it, get everything patched and all this, and then go to town and say, now just use it. No, you have to actually show them how to use the software, how to install it, how to get through all the bugs and all that kind of stuff. So we've got to do that, but we've got to get them all together at the same time now, and they've all got their own computers, and we don't have like that computer room. So what do? So we get a bunch of power cords, and then just transform the regular lecture room, basically like this, into a computer room. We just say, okay, Wednesday's Mnova day. You're going to come in, and we're going to start working with it. We're just going to lay out all the power strips. Everybody plug your laptops in, because you can't assume that the grad students' computers will last for an hour on their old batteries. So we set it up, and it was great. We could go through things. We discovered a lot of hurdles, a lot of bugs where people said, we told them to use the latest version of the software. A lot of them were using older versions for whatever reason. And so we encountered some practical difficulties, but then we got to sit there and work through them all. And at the end of the day, everybody knew how to use it, and was working on their own computer. So they had a tool that they could then use in the course, and then take that off into their own lab, which was very powerful. Training was also easy, because I'm fundamentally sort of lazy. And I had already been talking with Chen Peng, who's in the back, and he had already given us, he's really good at training, and so I started talking to him to ask for figures and slides, and he gave me a presentation. I said, okay, we're just going to walk through this with Chen's slides. And so the human resources at Mestrelab are also fantastic, and they've been very supportive of this effort. One of the other features that using software like this allowed us to do is to use a textbook that supplies spectra along with the textbook. So if we're using this organic structure determination by Simpson, and if you talk to the publisher and say, I'm going to be using this in our course, then you can go to the website, you can download all the spectra from for every one of those problems and a lot of the examples, and then we can say, all right, everybody, I put a tar file up on the shared drive. Everybody's now got to go download that tar file and process that data, and you solve the spectrum. So you're not working on the photocopied sheets anymore. There's no paper trading hands. Nobody's got to get out a little triangle and stuff like that. But you actually you start processing the textbook data as an exercise in class in exactly the same way that you do with your research data, and so that also eases that transition. Okay, so one of the innovations that we introduced in this course was to develop problems that basically came from the labs themselves, so the senior students. So I just recruited a bunch of the senior students who had gone through earlier versions of this course before I came to Northwestern, where we'd say, okay, somebody would have a starting material and a spectrum, and we'd give them the spectrum, and then they've got to figure out what the product compound is. So this I thought was a really good approach. This would be a very good mimic for how they actually operate in lab. Because ultimately the synthetic chemists are trying to do is see if their reaction came out right, and if it didn't come out right, they've got to figure out what the real answer is. So I could go to the senior students then, and these recruits, I would have them give me a chem draw and all their data, and then I would just transform that into a problem assignment just by tarring it all up and posting it on the web, on the shared drive, and then giving them to Mestrelab. So we included this in the courses lab. So we had to go through a few different labs: basic training, structure identification, where you basically just mimic the sort of characterization that you would have in your lab. You go through and take the standard canon of assignment spectra. And then we sit down at the spectrometer and kind of guess at what the structure should be, and then as homework you have to go through and assign all your peaks. So using this instrument that we got, everybody gets a full set of data for their own particular sample, and so we set this up in automation so everybody's data gets acquired in the night queue and then emailed to them automatically, and then the next day or the night before it's due, then they'll process it and turn in their homework as a Mestrelab file. Then the last lab that we ran, they were conducting a reaction in the magnet, and then they used the reaction monitoring software to analyze it. We'll get into more of that in a little bit. Okay. We also use this in the standard kind of unknown projects, where we actually, in the first project, everybody was working on the same data, and so we just gave them one big Mestrelab file for the data, and then they would go through and they'd assign it themselves. So basically, by the end of that, then everybody was really had the mechanics of working it. So that was all the mechanical stuff, but it's also really good as Mestrelab proved to be very good for pedagogy. So it was really useful for teaching concepts. So this was the old way that we would have for teaching about window functions, apodization functions. Maybe it's been a while, but a lot of the synthetic organic chemists I've encountered aren't even aware of what a window function is. They just they put their sample in, they get their spectrum out, and the spectrometer did something to it. And so I thought, okay, great. These guys are scientists. They'll enjoy math. So I got out the Brigham Fast Fourier transform book, and I showed them Fourier transform pairs, and I taught them about convolution, and that's how I did it for 2 years. And man, that was bad. That was a total flop for these students. So I needed to figure out a way of getting the message across to them better. So in Mestrelab, we could just pop it open, or sometimes I would just bring my computer and I would just work with the data and we would show it. So we had, so I'd show an example of a spectrum, and I'd say, okay, well here's this window. What can we do with different window functions? So I say, okay. We apply an exponential function of so, and take a look. The spectra are different, and all of a sudden it clicks. And so it was a really useful teaching tool that people could connect to. Okay, I was able to convey, to talk about things like strong coupling this way, because the NMR predict software allows you to hold and drag peaks that are coupled to one another. So you say, okay, I got to have this molecule here. It's got such and such a predicted spectrum, all right, where these are two methylenes. Well, then if I just grab one and move it over, how does the multiplet change structure? And you know, this really beats the whole. You know, I'm used to standing in front of class and saying, okay, well, this is what it means. You know, as you can tell, I wave my arms a lot, and so I would do this, and I'd say, okay, it goes like this and like that, and they kind of say, okay, Josh dances. But now they can take a look at this, and they can actually see what this really means, and so they're prepared to see it again. So we like to think that we're developing skills. When these students come in, they don't really feel the connection between proton and carbon assignments. They're very decoupled because they usually see them as like one sheet of paper and a different sheet of paper, and they know that maybe they think about the HSQC as a tool that can correlate them, but I used to still see all the time where people making assignments that made no sense if you just whereas it would if you just looked at the HSQC. So Mestrelab really helps with this because it draws you little lines. You know, you start making assignments, it draws you little green lines on your 2D spectrum. Not only that, but in class you can actually run this where if you've got everything set up and correlated, if you make an assignment to your proton and you've got your HSQC opened up, it automatically assigns the carbon spectrum or the carbon peak. And that's really great because it used to be that we would just say, oh, this is quote automatic, and now we can remove the quotes, and that really brings the message home to them. Okay, so this is one such example. Some of the figures here are just photocopies of the assignments that the students have turned in. Okay, so you know, this is really great. We've got all these assignments, and this is also a way that the students can look at this and say, you know, give it a reality check to see if they were right before they hand in the homework. One of the other nice things about this software is that you can use this for this multiple analysis. And this is what we've been seeing all morning. This figure was made with an earlier version of the software. Maybe the latest version would be able to totally get this. Maybe, but if you take a look at that multiplet, and then you can create this the predicted what the predicted appearance of the predicted multiplet should look like. You can automatically see, okay, these two things don't really go together, right? That there's something wrong. There's something that we don't understand. So now you've got to use your brain, which is what we're trying to get people to do in graduate school. So using your brain, maybe you actually look at the multiplet structure and think about what kind of multiplets your molecule could make, and then you kind of jimmy the parameters around and say, okay, what you start saying, okay, well, maybe this is a DQD type structure, and you have these different coupling constants, and you fuss with it until it all matches. And so so by this process of saying, you know, trial and error, and this iterative thing, we get to actually teaching the students. This just reminded me of one of my favorite Feynman quotes, of course, that which I cannot create, I do not understand. So by creating a multiplet using their brain, we think that they're actually understanding something. One of the skills that we've hoped to develop is some kind of sense of deconvolution. So this, one of our unknown projects here, there was a student who took a look at this peak right up here, and because he was now accustomed to putting in the shaded multiplets for the predicted spectrum under there, he could see that this peak looked a little bit broader at the base than was supposed to be, and everything else had a really good line shape. So, and it was kind of integrating funny. So, you know, he didn't know what this compound was, but he thought, you know, this might be some kind of an amine. And so based on that, because he was able to see that something wasn't quite matching up with the theoretical model that he had, he ran what we were trying to make into a normal sort of experiment, and because we've given them preset buttons in our new Agilent system, that he was running a proton nitrogen HMBC, natural abundance of his unknown compound in the course. And sure enough, we got a peak, and so that told us right away that yes, there was just like a really low broad amine resonance there that explained the data. So we were really happy that he went on to that. Okay, you know, we of course we want to develop the skill of spectrum assignment, although you know we still want to teach them that, so we don't want to necessarily you know, have them do everything completely automatically. They should. We feel like they should know what's going on, but eventually, maybe 5 to 10 years from now, Santi will have everybody in the class just assuming that they can just plug in their data and get a structure out, and with all the impurities identified. But for now, we want to teach them to like actually what's going on. So we've been kind of shifting these modes. We've got you know, the old way of analyzing this data. We have our cozy toxy, do a lot of tabulation, and now basically the first step in that these students learn how to perform their analysis is perform your multiplet analysis. You know, that'll automatically get a lot of integrations. It'll get your splitting patterns. It'll do all kinds of different things for you. And then you go through, so you do your multiplet analysis, then you go straight to your HSQC, you identify your methylenes, you do all these different things that make that have traditionally made a lot of sense, but it's a lot easier now that they've been using the software tool. One other skill that I've always tried to teach them is indirect chemical shift referencing, and now Mestrelab is able to do that. And so that's a very useful thing, because a lot of times people, especially if they're taking, say, proton nitrogen data, or a lot of them are now doing proton silicon HMBCs, proton phosphorus HMBCs, and they don't know what to do. You know, they want to get precise chemical shifts, but now they're able to, because they can do the indirect referencing. This improves the quality of reports that they produce. That's another thing that we're trying to teach in this course. So this is what the reports used to look like. So there's this one lab where, and this is less than a year old. So this is not ancient history, but this is this student prepared this molecule, and the boss has them fill out this form this way, and you know, they have you know, they write out their entire spectrum like this, and then they draw a little. This is time consuming, and it's not like it's not something that can be propagated except by a photocopier. So now we teach them to take your ChemDraw. Mestrelab allows us to paste everything in JAX format, and they can create tables, and so basically we've ingrained in them to create real nice looking reports by doing their homework just this way over and over again. This is their homework and lab reports, and now they're all totally set to give their boss better data or a better report, and they're prepared for publication really easily. Okay. It's also very easy to grade them this way. Okay. So it also improves their spectrum presentation, where instead of something that looks like this, you know, you're not quite sure exactly what's going on. It's not that super informative. Here we get something that's pretty standard, that where we have that unknown compound where we had an impurity that we needed to identify. We didn't know about that when we assigned it, but now you can actually take a look at this, and you can see all the assignments. You can see chemical shifts to a high number of significant figures in their numbers. It's also improving our presentation of 1D NOE data because all the assignments appear as little green numbers over the spots. So if you're looking for the presence or absence of an NOE at a particular chemical shift, you can say, okay, well, there's nothing there at number 7. So that's really nice to have that 7, even though there's nothing there right there. That also makes it easy to grade. Also, presentation, it allows us to do the kind of cuts, so we don't have one giant spectrum with a couple tiny little specks here and there, but now you can actually focus in on the relevant regions of the spectrum. Okay, reaction monitoring. This has turned out to be taking off at Northwestern. Okay. We figured that this would be a key skill for organic chemists to develop. You know, they're running reactions all the time, and a lot of them are measuring rates. But you know, most of the time they're just not doing it. This is something that they don't do because they think it's hard. And so if it becomes easy, then they might actually do it, and their science would benefit. Okay, so I figured that this would be an important part of the course, and I started reading the Mestrelab manual and found that there was this module for doing this. I went through, I'm preparing for the course at this stage, and I wanted to find a good reaction. I queried AMMRL for a reaction that would satisfy the design criteria. You know, you have to be able to perform it at room temperature. It's got to be able to be complete within a lab period. Easy preparation, just mix and go. And the reactant and product peak can't really overlap significantly. Okay. So my colleague Andrew Mobley at Grinnell College came up with a really great reaction that we want to write up in JChemEd. And basically, it's just the Finkelstein reaction. That this is a very standard organic chemistry reaction. These are photocopies or these are scans of the students' reports, where we have a reactant, and a product, and so you get one peak goes to another, and it worked out really well. So we go through this whole protocol, which I'm going to skip for reasons of time. And so we'd bring this all into Mestrelab. So we were taking one spectrum every 30 seconds for an hour or two, and we got quite a lot of data. One of the first things that we teach them is to use the decimation tool. So instead of seeing all the spectra at once, we can go over and go like this, and we can say, okay, well, here's your reactant, and it's going away, and your product peaks are coming up. You know, now we're going to calculate the fit, and actually, so you fit that, and then you can actually get a rate, which is really cool. So all they've got to do is bring in their data, run through a short analysis, and now they're going to get a reaction rate. They can measure the rates of both product loss or product formation and reactant loss. And so now this is what one of their student reports looks like. So they calibrate their temperature. We need to make sure to ingrain in them that they've got to calibrate their temperatures. And they basically just cut and paste their information directly from the reaction monitoring module. You know, we actually ran this experiment as a VT experiment. So we kind of divvied up the labor so that we'd sort of do some physical organic chemistry. So each lab section ran their reaction at a different temperature, and then as a collaborative effort, once we had gotten all the data together, then everybody got their reaction rates and plotted them in an Arrhenius plot to get activation energies and thermodynamic parameters. So I thought that was really cool, and you know, this data just looks great, that was really satisfying. Okay, so that really connected with the students. That you know, they could that was something that they didn't know that they were going to do coming into the course, and then they left the course thinking that they had learned something useful. So this one student I had encountered He's going off into some synthetic lab and they make catalysts, but nobody actually measures any reaction rates. And so now he's saying, well, gosh, if all I do is just measure the efficiency of my catalysts by actually measuring the reaction rates, that'll be a great thing for the lab. That'll be really good. Okay. The prologue for this, now that the course ended the course was in the winter quarter. Since then, I've found one of the students coming in over and over to one of the spectrometers here, running reactions, and so I said, hey, what's going on? So it turns out that he really has gone to town with this. That he took what he learned in the course to study this ubiquitin ligase enzyme, which I can't say too much about because it's not really reported yet. But they're now screening for inhibitors by monitoring reaction rates. So instead of looking at binding or looking for peaks to shift, they're saying they're running a reaction for every one of the potential inhibitors. And so you've got some nucleophile in the enzyme, and they react it with an electrophile, and they say, okay, how fast does that thing react? Then they run another one. How fast does that one react? They do this, they're doing this over and over and over and over again. And basically, the only way they'd ever even have considered running this, running their research this way, is they needed some easy way to measure a rate. And now they've got one, and so now they're going forward with it. And so it's a brand new screening tool for them. And so that's something to see, which is very satisfying. Practical tips for how to implement this if you wanted to do this in your institution. You can have me come by and implement it in your institution if you'd like. It's important to have a site license so that everybody can use it, and then they can go off into their labs to continue using it. You got to make sure that all the students are on the same version of the software. You got to spend a good full class just figuring out, making sure that everybody's on the same page. There's certain IT hurdles involved here that we discover that the IT knowledge of some of the graduate students coming in isn't necessarily that high. They don't know about file compression formats and things like that. So they don't necessarily know about FTP. So you got to coach them a little bit on that. But then that's more teaching, and that's fine. The other thing is to encourage them to get a 3-button mouse. A lot of the Mac users don't have anything like that, and so that's that's a key point. Just say, okay, buy one, and I can vouch now that the Apple Magic Mouse, even though it doesn't look like it has multiple buttons, actually does work with Mestrelab, so that's good. Okay, and if you're going to teach this way, first thing you do is to teach them how to make their defaults good, so that everybody can read it, and so you have a kind of a standard format in class. Also, you, the instructor, need to provide a chemical structure with the proper numbering. Otherwise, the whole class is going to have different numberings on their compounds, and that's going to be terrible to grade. The other thing is that, unfortunately, because this is software, it's easily copied. You do have to be alert for cheating, because if you've got one person's Mestrelab file, if it's correct, is probably going to look just like that of another person's. So, you gotta keep an eye on that. So, thanks for your attention. I'll take any questions probably a little bit.
Thanks very much.